Good morning and welcome to the second of 6 videos into statistical inference. I'm Justin Zeltzer, and yes, while this is early morning for me on a Monday, you might be watching this late at night or sometime in the afternoon, but saddle up because we're going to deal today with maximum likelihood estimation, or MLE, including all of the subtopics within. Now, we're taking as read at this point the concept of likelihood itself. That was dealt with in the first video. If you haven't seen that, feel free to go and have a look at that. It should be up on zedstatistics.com, or if you're watching this at university, just look at your previous module. But going through the flow of the slides we're going to be looking at today, initially we're going to look at just the definition of maximum likelihood estimation, followed by a quick example of a discrete distribution. In this case, it's going to be a geometric distribution of pregnancy attempts and success from artificial insemination. From there, we'll look at concepts of score and information, score being the first derivative of the log likelihood, and the information being just a modified second derivative of the log likelihood. We'll see why those two concepts are important. We'll then look at some properties of maximum likelihood estimation, including whether the maximum likelihood estimate is explicit or implicit. We'll be looking at biasness and consistency, asymptotic efficiency, and also the concept of invariance. And if all that sounds like a bit of a mouthful, we'll saddle up because you're about to become well-versed in all of it. And in the process, becoming more impressive to fellow nerds you might meet at any given social event. We're then going to have a look at parameter transformations, which takes one of these concepts from the properties of MLE slide here, that being invariance, and looks at it specifically. We'll deal here with the log odds transformation, which is quite common in probability, and we'll see how the MLE deals with log odds. We then move on to looking at multiple parameters. So if we're trying to estimate numerous parameters at the one time, we'll see how MLE deals with that. And that'll lead us on to looking at another example. In this case, a normal distribution. So we'll have 2 parameters to estimate. And that'll be a good chance for you to try your hand at generating your own MLE. And finally, we'll have a very quick look at some other estimation methods and how they compare to MLE. All right, so let's begin with maximum likelihood estimation, MLE. Now, this sentence is one that I'd like you to read 3 times. It almost reads like a tongue twister, but it's actually very simple. MLE provides the parameter value, or values, that makes the observed sample the most likely sample among all possible samples. Whoa. So just let that one sink in for a second. Now, if you've watched the previous video in the series, you'll remember me talking about something I termed a flip in logic. And this relates to that. Because in reality, we only ever have one sample. So it seems a bit of a misnomer to say, well, let's make this the most likely sample because we only have one. But what we do is we play around with potential values of the parameter and stop when we find that value of the parameter that gives us the highest probability of generating that sample that we got. So in technical terms, we can say that theta hat, which is our estimate, is a maximum likelihood estimate if the likelihood function at that particular value is greater than the likelihood function of any other value in the parameter space. But I'll give just a quick note here that when we use the acronym MLE, it can refer to one of 3 things. Maximum likelihood estimation, which is the concept in its entirety. That's how I've been using it thus far. It can also be used to relate to the maximum likelihood estimator or the estimate itself, the actual number value. So depending on context, it'll be pretty obvious which one it relates to, but just keep that in mind. And this will be common with your textbooks or other resources that talk about MLE. Okay, so let's have a look at our first example here. Now, this involves pregnancy success from artificial insemination. So to start with, we've got these three variables. N is the number of couples, or alternatively, you can see that as the number of aspiring mothers. Y is the total pregnancy attempts by all couples, and theta is a probability of an individual pregnancy success. Now, this is our likelihood function for this scenario. You can see that it almost looks a bit like a binomial function there, but it's actually born out of a geometric probability distribution. Now, if you don't care what a geometric function is, because I guess this video isn't really about explaining different types of functions, then feel free to skip the next slide. But if you're anything like me and you're not satisfied with a wave of the hand, then I'm going to spend the next minute just explaining how we got this function, this likelihood function, from our geometric probability distribution. Here I've defined a variable y subscript I, which is the number of attempts, pregnancy attempts, required for couple I before their first success. Now, given this is a probability distribution for yi, we had to set a fixed population parameter, a fixed population probability of success at 0.15. So for every given pregnancy attempt, there should be a 15% chance of success using artificial insemination. So what's the probability of a given couple having success on their first attempt? Well, clearly that would be 15%, 0.15. You can see that. The probability of them achieving success on their second attempt means that necessarily they've had one failed attempt first and then one successful attempt. So that's actually 0.85. That's the probability of a failed attempt times the probability of a successful attempt. So clearly, with each new outcome here on the probability distribution, we're multiplying by another factor of 0.85 because you needed one more failed attempt before the successful attempt. So we can generate from that a general equation here which applies for all possible outcomes, where we multiply that 0.85 by yi minus 1, and then finally we times it by the probability of a single success. So you can see this is why it's called geometric, because we are multiplying each time. Now, again, if you recall from last video, to find the likelihood, it's actually a product of all of these individual probability density functions. We're going to take this equation for every couple in our sample, and we're going to multiply them together. So you get the product of this 1 minus theta to the yi minus 1 times theta, which if you take the product of that, we can actually write here the sum of y minus n times theta to the power of n. So this likelihood reduces to this equation here at the end. And instead of writing the sum of y, sigma y, if I just write the letter y instead to represent that, so where yi is an individual number of attempts for couple I, y without a subscript is now the total number of attempts for all couples, we have our likelihood equation. So that's how we get this equation here. So I'm asking you now to sketch the likelihood function of theta and the log likelihood function of theta if 20 successful pregnant couples took a total of 100 attempts. So let's have a look. Now I've got on the left here the likelihood function, and on the right our log likelihood function. Again, both concepts we dealt with in the first video. Here it seems that the likelihood function peaks at around 0.2. Well, in fact, it's going to be exactly 0.2 where it peaks, which kind of makes sense. If it took 100 pregnancy attempts for 20 couples, the probability of an individual pregnancy success looks like it's going to be 1 in 5, doesn't it? Now, if you took the log of all the values on that distribution, which is in fact the log likelihood function, it would look a little bit like this. So it looks quite different, and you can see the scale is completely different. We're in negative territory here because we are now logging a very, very small positive number. And it's no longer that nice bell curve, but it nonetheless still peaks at 0.2. So I just wanted to put those side by side for you, so you can get a good sense of what a likelihood function would look like versus a log likelihood function. Now, what the rest of this lecture is going to be concerned with is trying to find the peak of this log likelihood function and also how sharp the peak is. In other words, how much confidence do we have in this being our maximum likelihood estimate? So of course, it's going to involve quite a bit of calculus. We're going to take the first differential and set it equal to 0 to try to find the turning point. And we're also going to take the second differential to assess the curvature. And the higher that curvature, the more confidence we're going to have in our maximum likelihood estimate. So that leads us to the score equation. And as I said, to find the maximum likelihood estimate, we need to differentiate this log likelihood equation and set it equal to 0. Now, you might be asking at this point, why don't we just use the likelihood function? Why do we bother logging everything first? Well, no particular reason, except that the log likelihood function tends to be way easier to differentiate than the likelihood function. We'll see that a little bit later on when we actually get some hands-on experience at all this calculus. But believe me, if you want to give it a go, feel free to try to differentiate the likelihood function at any given point, and you'll see that it is not a fun job. And of course, it doesn't matter whether we're maximizing the likelihood function or log likelihood function. It's actually going to provide us the exact same solution. And we saw that on the previous slide. Remember those two probability curves that peaked at the same point? Well, that happens because the log function is actually an increasing function. Anyway, let's continue. So we set the differential of this log likelihood equation, we set that equal to 0, and this is now called our score equation. So in solving that, you will find your MLE. But we're not just concerned with finding the MLE. We want to know how confident we are about it. And I've written here that our confidence in the MLE is quantified by the pointedness of the log likelihood. So if you recall those graphs from the previous slide, the pointier or the more peaked our log likelihood function, the more confident we are in our MLE, and thus the smaller our confidence intervals we will create. So what we can do is we can construct this thing called the observed information, which is in fact the negative value of that second differential. If you appreciate that the second differential will always be negative within itself because it's a concave down curve, then by putting a minus out the front, this will become positive again. So the higher the value of this observed information, the higher our confidence we have in our MLE. Now, there's a little bit of a trick we still need to do here because it's not as if we can just use the sample value here in our log likelihood. What we do is we take the expected value of all possible samples. So this becomes our expected information. So you can see here we've got a little subscript O for our observed information. Here, without that subscript, this is the expected information, also called Fisher's information, if you'd like. But this is the crucial metric that we need to construct confidence intervals. And why it's so important is that the variance of our estimator is in fact the inverse of this expected information. So while we have our maximum likelihood estimate provided by the score equation, we also have the variance of that estimate provided by the information. It's the inverse of our information. So you can see that the higher our information, the lower the variance of the estimator is going to be. So in other words, the more confident we are about the location of that MLE. So let's have a quick look at an example here to see how this plays out. But here is that pregnancy success example and the likelihood provided there. Now to take the log of that likelihood, I'm not going to go through all of the log laws that got us this equation, but you can take it from me, that is the log of the likelihood above it. Now, if I'm going to try to find the MLE, where n is 20 and y equals 100, and calculate a 95% confidence interval, well, I'm going to need to differentiate once and differentiate twice to find this information. So the first bit's probably the easier part, which is where we differentiate the log likelihood function. And the differential of this log likelihood is just going to be n on theta for this first term. It's going to be y minus n over 1 minus theta for the second term. Of course, there'll be a negative that comes out the front from that. So we set that equal to 0. And in doing so, we can find an estimate for theta, which we're going to term theta hat. And if you rearrange that, you'll find it's n on y, which is 20 on 100.2. All you need to do is just rearrange this equation and solve for theta. Now that's the easy bit, I'd say. What we're going to do next is have a look at how to find the confidence interval, or put more simply, find the variance of that estimate. So here's our observed information. It's the negative of that second differential. So if our first differential up here is provided as n on theta minus y on n divided by 1 on theta, if we differentiate that again with respect to theta, we get this equation here. And if all this is a little bit frightening for you, I might put in the notes of the video a link to some good videos on calculus and log laws. And if we get rid of a lot of these negatives that are popping up here, if I sort of net those out, we get n on theta squared plus y minus n over 1 minus theta all squared. And this is our observed information. Now the expected information is actually going to be the same thing, except we're going to use the expected number of pregnancy attempts instead of the observed number of pregnancy attempts. In other words, we're going to express this value y in terms of n and theta, both of which are considered constant terms. So you can see now this expected information only has n's and thetas in it. So we've taken it completely out of the realm of the observed sample. And that's a really good thing, as it means in theory, our expected information no longer is affected by the vagaries of whatever sample you happen to get. It relies only on n and theta. So if theta was, say, 0.5, and there were 100 couples, then you'd expect 200 pregnancy attempts. So again, this reduces to something a lot simpler, which is just n on theta squared times 1 minus theta. Again, I've skipped quite a bit of algebra there, but hopefully you're up to that challenge. So in constructing a 95% confidence interval, we have n on y, which is going to be our estimate up here of 0.2, plus or minus 1.96. Where do we get 1.96 from? Well, the good thing about MLE, as we'll find, is that when n is sufficiently large, the MLE will have a normal distribution around it. So this is simply the value from the normal distribution at 95%. And in the square root here, we have the inverse of the expected information. Don't forget that the inverse of the expected information is the variance of our MLE, and the square root of that is the standard error, which goes into our confidence interval equation. And if we sub in all the numbers provided, 0.2 being our estimate and n being 20 for 20 couples, we can get our confidence interval at 0.1216 to 0.2784. So while our estimate was 0.2, so 20%, we have a 95% confidence interval around that estimate that goes from 12.1 or 12.2% to 27.8%. All right, so let's carry on to properties of MLE. Now, the first thing we're going to look at is whether the MLE is explicit or implicit. Now, the distinction there is that if it's possible to solve the score equation, that's that first differential equation, if it's possible to set that equal to 0 and solve, then we say that the MLE is explicit. But sometimes that's not possible, so we'll need software algorithms to help us out to calculate or to generate the MLE expression. And when that happens, we say that it's implicit. Nothing functional changes or hinges on our classification of explicit or implicit MLE, but it's just good terminology to get under your belt, particularly because if we have an implicit MLE, it might imply that you need a lot of computer power to generate the MLE, particularly if you're estimating numerous parameters. Next, we're going to look at biasedness and consistency. The first thing to note is that MLE is not an unbiased estimator. Biasedness here means that the expected value of the estimator is the thing that it's trying to estimate. We're going to see an example of this a little bit later on, but this shortcoming is generally not particularly too fatal to the usage of MLE, because when you have enough observations, MLE becomes asymptotically unbiased. So with more and more observations, whatever bias exists just fades into insignificance. And it's also consistent, meaning that in large samples again, it converges on the true population value. Now, you might be thinking that asymptotically unbiased and consistent sound like they're pretty much the same thing. And to be honest with you, when I was doing a little bit of research before this video, I had a look online to make sure I understood myself the distinction between the two. And this example is probably the best way of appreciating the distinction. So let's just, for the moment, sidetrack a little bit. Let's just presume we have this estimator phi, and it's equal to the first value of x plus 1 on n. Now, as n becomes infinity, or n gets really, really large, this will become unbiased. So it's definitely asymptotically unbiased because the first sample value is itself unbiased. But it's not converging on the true population parameter value. So it's not consistent, this particular estimator. So while it's true that these two qualities of an estimator tend to go hand in hand, there are probably unique situations where they don't. And hopefully that's at least provided you with that distinction. The other good thing is that the asymptotic distribution is normal, which is great for confidence intervals because it means you get to use the standardized normal distribution. Makes things real easy. So it's distributed normally with an expected value of the true population parameter value, which is great. And it has a variance of that inverse information metric that we saw previously. Here's something else. It's also asymptotically efficient. What does that mean? It basically just means it has the smallest asymptotic variance possible of all consistent estimators. In other words, it's the best. MLE is, we say it's optimal, and it's true that it is the best or optimal in all but a handful of unique situations. So one example where it potentially might not be optimal is where the likelihood function might peak outside of the relevant parameter range. So think about a probability that needs to be between 0 and 1, right? It's quite possible that the likelihood might peak either side of 0 and 1, so in the negatives or in probabilities greater than 1, which of course doesn't make logical sense. But if you just applied an MLE to it, it might give you the wrong result. But for our purposes, we can kind of think of MLE as the golden child, the one we're going to pin all of our hopes and dreams on. And the final property of MLE that we're going to talk about is something called invariance. Now, this is immensely useful. It's provided by this very simple formula that basically says if you take a function of the parameter, the MLE for that function will just be the value you get when you sub in the original maximum likelihood value. So let's just decode that for a second. Say you found the MLE of some kind of parameter and it happened to be this theta hat. If you wanted to get some kind of function of that parameter, it's really easy to find the new MLE. You don't have to go through and recalculate a new maximum likelihood. You can just sub that value into this function that you've created. And we're going to see that in action in the very next segment of this video. So let's have a look and see how that plays out. But again, it's an extremely important feature of maximum likelihood estimation. Leading us on to parameter transformations. So log odds might be something you've heard of before, especially if you've done anything to do with binomial logistic regression. But it's generally provided as a function of theta. It's the log of theta over 1 minus theta. So g here represents that function of theta. So if the MLE for theta is theta hat, then the MLE for the log odds is going to be, well, the log of theta hat over 1 minus theta hat. So as I said, you don't need to recalculate a new likelihood function, differentiate again, and do all that stuff. You just plug in the values into this function, which is quite helpful. The next question then becomes, well, can we go from the standard error of the original MLE to the standard error of this new transformed parameter? And indeed, we can. So if you've got the standard error of theta hat, and this applies in large samples only, but that's okay because we tend to have large samples. If it's the standard error, some kind of standard error of theta hat, then the standard error for the log odds is given by this. And this is a general equation that you can always apply. The standard error of a transformed parameter is equal to the first differential of that transformation function times the original standard error. And this is achieved through something called the delta method, which I'm not going to go into in this video. But again, I'll try to find a nice explanation on YouTube, and I'll post that up in the notes of this particular video. So you can have, if you're keen enough, you can check that out. But for the purpose of our course here, all you really need to know is that this is how you get your standard error of a transformed parameter. So in this case, we have the original standard error of theta hat, and we're going to multiply that by the first differential of that transformation function. And here's the transformation function. It's the log of theta on 1 minus theta. So if you're going to take the first differential of that function, it requires a little bit of algebra, but you can trust me here, it's going to be 1 on theta times 1 minus theta, or if you sub in the MLE, it's going to be 1 on theta hat times 1 minus theta hat. But hopefully you can see how convenient that is, this principle of invariance, and also the ability to calculate a standard error on this transformed parameter. Shall we move on? At this point, we're going to check in with our good friend Jupyter again. That's multiple parameters. For some reason, I always make this bubble the biggest one. But it should be no stretch of your imagination to appreciate that while we've been dealing with single parameters, MLE can apply to numerous parameters at once. So if you have a likelihood that involves numerous parameters, you can find an MLE of all those parameters. Now this is what we've been looking at so far. The MLE is distributed normally in large samples with the mean of theta and a variance, which is the inverse of the information. But this doesn't need to be a single scalar or just a single value. It could also be a vector of parameters. So again, the MLE is distributed normally as a vector of length p. And this parameter theta now can be considered a column vector of individual parameter values. And guess what? This information, or the inverse of the information, is now a matrix. Well, because we're going to have a whole bunch of covariances as well. But let's take it a step at a time. So in this case, theta is a vector. I've put this as a column vector here. Theta 1 down to theta p for p parameters. Now to find theta hat, which itself is a vector, theta hat solves a bunch of simultaneous equations. So you're taking the log likelihood function and differentiating it with respect to each of the parameters in turn and setting all those partial derivatives equal to 0 at once, and then solving for all of your parameters. Fear not, we are going to deal with this in an example. But that provides you with this theta hat, which is a vector of individual parameter estimates. And as I forewarned you, the information is in fact a matrix here. So this is our information matrix. And it's going to be a P by P dimension matrix, where each of these individual terms, each of these individual elements of the matrix can be written as this function here, which is the negative second differential of the log likelihood, where you differentiate with respect to each pairing of parameters that you're estimating. And for the sticklers out there, you're correct. That's in fact the observed information. You'll have to take the expected value of each of the elements and, of course, then invert the whole matrix to get your covariance matrix, which is maybe just a tad beyond this video. But that's at least the theory behind using multiple parameters in your maximum likelihood estimation. So it might be time now to check in and do something a little bit more concrete by way of an example. Now, this is the same example that we used in the first video in the series. It's about systolic blood pressure in pregnant women. We have a sample of 5 pregnant women that have their SBP, their blood pressure, taken, and it's considered to be normally distributed. And here indeed is the sample of 5 blood pressures that were taken. The question might be, find the maximum likelihood estimate for mu and sigma. Now, if you're feeling up to it at this point, I would advise trying to do this yourself. Get a pen out, get a piece of paper out, and see if you can come up with the maximum likelihood estimate for these 2 parameters. We're not going to go as far as the information matrix in this example, but see if you can get at least the MLE estimates. And if you ever need a hint, feel free to just push the video on just a little step, and you'll see me do the next little bit, and then you can pause it from there. That's probably the best way of getting the most out of this section in the video, I think. Nonetheless, from the last video, recall that the probability density function for a normal distribution is this lovely looking fellow here on the right in turquoise. It's got sigma squared in it, it's got pi, it's got mu. It's utterly delightful. And to find the likelihood, we have to multiply this. We have to find the product of this across all the observations. And indeed, that's what this tells us to do here on the left. So if we open that out a little bit, with n being the number of observations, we get this being our likelihood equation for mu and sigma squared. That's 2 parameters for which we're finding the likelihood. Now you might recall this 3-dimensional plot I made from last week, which is a visual representation of this likelihood function. Now there's our sample. Our maximum likelihood estimate is defined by the peak on this 3-dimensional net. And it will have 2 values, a maximum likelihood value for mu and a maximum likelihood value for sigma. Now you can get these 2 values just simply using computer software. But I kind of just wanted to show you straight off the bat what we are trying to achieve. We're trying to find the values of mu, which is this axis here, and sigma, which is this axis here, which maximizes our likelihood function. So we're going to have to take the log of this delightful likelihood. We're then going to have to differentiate with respect to mu and sigma respectively, set both of those equal to 0, and solve simultaneously. Whew. Are you up to that? Let's give it a go. Deriving an MLE for a normal distribution. Find the log likelihood. Here we go. There's the likelihood equation written again. Now this is the log likelihood. Again, I'm not going to go into too much detail as to how this comes from the likelihood here. Hopefully your skills in logarithms are up to scratch. But what I have done is I've expanded the brackets here from this y minus mu quadratic. So you can see I have the sum of y squared minus 2 mu times the sum of y plus n times mu squared. The n term there results from the fact that we're summing across a constant term, mu squared. All right, now we need to find the differential of this log likelihood with respect to mu And we also need to find the differential of that log likelihood with respect to sigma squared and set them equal to 0. So here we go. Differentiating this equation with respect to mu, well, we could ignore the first two terms here because they are completely mu-less. And in reality, there's actually only two mu terms here. So we'll get 2 times the sum of y minus n times mu all over 2 times sigma squared. So again, it's a little bit algebra intensive, but setting that equal to 0, you'll appreciate that it's only the numerator which is going to help us out with that. So we're going to set this numerator equal to 0. And quite simply then, our estimate for mu will pop out as the sum of y on n. If you just rearrange that equation when you set that equal to 0, you'll get this neat little equation for mu. And conveniently, this makes intuitive sense. It's just an arithmetic mean. Now, the tougher bit is going to be differentiating the log likelihood with respect to sigma squared. So in that case, we're going to have a couple of terms here. We'll have to involve this term here because we've got a sigma squared for this bit. And we've got 3 additional terms out the back as well. So it's going to get a little bit gross. Now, and it's possible too to differentiate this with respect to sigma, but to make it easier, I'm going to differentiate it with respect to sigma squared, so that we'll have an answer in terms of our variance, which at the very end we can take the square root of to get our MLE for the standard error, if we so need it. Anyway, this is the differential of this equation with respect to sigma squared. We now have a sigma squared term here, but that's okay. There's nothing wrong with that. And if you were to rearrange this, of course, this first term would come across to the other side. You could multiply both sides of the equation by sigma squared, do a little readjusting, and you'll find that our estimate for sigma squared is this equation here, 1 on n times all this stuff. Now from this point, what I'm going to do is I'm actually going to sub in, instead of having mu there, I'm going to sub in the sum of y on n. And I'm going to do that for both of these terms involving mu. The reason being, we are solving simultaneously. So the answer from the previous equation can get bunged in right here. So if you'll indulge me just to do that, you'll see I've got the sum of y on n here, and this will become the sum of y on n, which will get squared. So it will reduce to an equation that looks a little bit like this. And you'll notice that this middle term is actually just 2 of the final term. So they'll be able to, one of those will be able to cancel out. And eventually you'll have the sum of y squared on n minus the sum of y on n all squared. And this is going to be our maximum likelihood estimate for sigma squared. And if you chose not to eliminate that mu hat character up in this first line, you might get something that looks a bit like this, where you've got y minus mu hat squared. Now this might be quite familiar to you. This might look to you like a fairly typical estimate of variance for a continuous variable. But I dare say there's probably one difference to this equation from the one you would have seen in your very, very fundamental studies of statistics. Remember how they always told you that it's n minus 1 on the bottom? Well, in this case, for MLE, it's not n minus 1. It's just n. MLE is not an unbiased estimator. Remember that? To be unbiased, it needs to be divided by n minus 1. But this is, I guess, proof to you that MLE does not provide necessarily an unbiased estimate. Anyway, there are the 2 forms of your variance that you could have, the 2 forms of your estimated variance that you could have got from this. Now, of course, we haven't actually put in any values yet. We've just got sum of y's and n's on everything. Yep, but the next bit's going to be pretty trivial. It's just going to be using these 2 formula and subbing in the values that we got from our sample. So that's going to be pretty easy indeed. Let's do it just to make sure we're all on the same page. The MLE, the maximum likelihood estimate for mu, is going to be the sum of y on n. And if this is our sample, we can find the sum of y is 590 and the sum of y squared is 70,258. So I'll trust you to be able to chuck in those values into these formula, and you'll find the estimate for mu to be 118 and the estimate for sigma squared to be 127.6. For sigma, it's 11.30. And there you have it. I'm glad we got through it. Now, that might well be the end of this lecture, except that I might have a quick look at some other estimation methods, or at least giving you the pros and cons of MLE with respect to these estimation methods. You may be familiar with OLS, or ordinary least squares, as an estimation method. We use that predominantly in regression. There's also something called method of moments. And while I'm not going to go into depth into how these actually work out, I might just mention here that the advantages of MLE is that it uses the distribution of y in developing an estimate. Recall that those probability density functions were actually integral in the calculation of our MLE. For both OLS and method of moments, you don't use the distribution of the underlying variable. You might use things like the mean, and for method of moments, you might use higher order moments. But the full distribution is what's used in MLE, and that's potentially a strong point. The disadvantages of MLE is that it's less convenient to calculate in certain circumstances. For example, when it's implicit. And it also requires distributional assumptions. So we've been saying all the way through that this distribution is assumed to be normal. So let's use MLE. But generally, that's not such an issue in large samples. It tends to be more of a concern when you're dealing with smaller samples. But yep, that's it. That is statistical inference number 2. Glad you could stick with me through it. For other videos and statistical resources, you can check out zedstatistics.com or any of these socials.